Hello, and welcome to the first of our lectures. This lecture will be chapter 13 in the Giancoli textbook on fluids. So we will be covering uh, density, pressure, Archimedes' principle, the continuity equation, and the Bernoulli equation. So if you're looking at a different textbook, those are the subjects that you should be looking for. So we will be going back and forth between lecture slides and a whiteboard so I can go over some examples from the book and basically some problems so you can see how the equations work. On a Tuesday, some more detailed problems will be posted, and those you're going to work on. And you can ask me for help. You can email me for help, or if you want to schedule a Zoom meeting, I can do that as well. But in the meantime, let's start off with the lecture. So we are starting off with, again, fluids before we go into electricity and magnetism, which we'll be spending most of the summer course working on. So when we say fluids, typically you might think of a fluid as simply being a liquid. So you drink your fluids when you're sick, for example. But fluids can be a liquid or a gas. Basically anything that can move if it's not confined to a specific space. It'll move around and has the ability to flow. So it can be a liquid or a gas. It's not a solid. It does not have a defined shape. And, like a solid would, for example. So liquids obey certain properties and gases obey certain properties. And we're going to look at some of the properties that they have in common. And we're going to start by introducing a property called density. Sometimes if you're talking about mass of an object with an indeterminate shape or size, like the air, for example, or maybe a portion of the ocean, or something like that, where it's not easy to measure the exact size or the exact dimensions of the section of the air or the ocean that you're looking at, you can still talk about it physically by referring to the ratio of the mass to the volume, which is the density. And a lot of times it's easier to work with the density directly than to work with the mass or the volume. And we'll talk a little bit about what that means. So the density is the ratio of mass to volume. And the original definition of the gram, the metric unit for mass, comes from how it was, basically comes from the mass of 1 cubic centimeter of water, which means the density of water in grams per cubic centimeter is 1 by definition. Or in SI units, which is kilograms per cubic meter, it's 1,000 kilograms per cubic meter. So, and that's by definition, although the definition of the kilogram has changed a little bit over the years, as is the definition of the meter, certainly to the precision that we're working at. And even given that the density of water can vary depending on how much pressure it's under or how hot it is or cold it is, that for our purposes, certainly for 2 to 3 significant figure precision, 1,000 is more than good enough for the density of liquid water. The density of air, being a gas, is much more variable because it changes very easily or very sharply with temperature, with changes in temperature or with changes in pressure. So at sea level and at a temperature of 0 degrees Celsius, the density is 1.29 kilograms per cubic meter. On average, the sea level temperature at the Earth's surface is a bit warmer than that. It's about 15 degrees Celsius. And so as a result, the density of the air tends to be a little bit less, that adding heat makes the air expand, which makes it less dense. And so the average density at sea level is 1.22 kilograms per cubic meter, not 1.29 kilograms per cubic meter. So that's a significant distinction. Certainly, if you're looking at meteorological applications, that's a significant distinction. So the density of solids and liquids varies very slightly with temperature and pressure. So if you're looking at salt water in the ocean, for example, the density doesn't get noticeably different from the density at the surface until you're very deep. You need to be a kilometer or two deep before you notice the difference in the density of the salt water relative to what it would be at the surface. And solids, yes, there's linear expansion, but linear expansion is actually very, very small, proportionally speaking. So the density doesn't change a whole lot unless you change the temperature by a very large amount. And the last term I want to mention is specific gravity. This is a term that was used a lot in the early days of physics when people talked about density, but they didn't have the metric system. So the specific gravity is the ratio of an object's density to the density of liquid excuse me, the density of liquid water. Now, in metric units, the density of liquid water is 1 gram per cubic centimeter. So if you're measuring the density of an object in grams per cubic centimeter, any object in grams per cubic centimeter, the value you'll get is equal to the specific gravity. And so density in the metric system has specific gravity more or less built in. In SI units, you don't use grams per centimeter. Generally, you use kilograms per cubic meter. And so there's 1,000 kilograms per cubic meter. There's 1,000th of a kilogram in a gram, but there are 1,000,000 cubic centimeters in a cubic meter. And so you multiply by 1,000,000, divide by 1,000, you get 1,000. So 1 gram per cubic centimeter is equivalent to 1,000 kilograms per cubic meter. So this table is in the Giancoli book. If you're using a different textbook, you're going to have a similar looking table in it somewhere in the section that talks about density. So we'll look at some of the numbers. So if you look at the metals, they're typically more dense than water. So water is 1.00 times 10 to the 3. The metals that they show are more dense than that, and so are concrete and granite. Wood tends to be less, so it tends to be 300 to 900 kilograms per cubic meter. And again, it depends on the type of wood. One of the consequences of that, because wood has a lower density than water, wood floats in water. And we'll talk a little bit about what that means. So water has a density of 1.00 times 10 to the 3 kilograms per cubic meter. You notice the metals have a higher density than that, and so do concrete and granite. Wood has a lower density, so basically 300 to 900 kilograms per cubic meter. So it's less than the density of water, which is the reason why wood floats in water. Notice also that ice has a smaller density than water. That's an unusual property of water, that as it goes from a liquid to a solid, it loses density, so it starts to expand. Once you get below 4 degrees Celsius, between 4 degrees Celsius and the freezing point, the liquid water expands, and then when it becomes solid, it has a lower density of water. And so ice floats on top of water, and that's actually very important. If ice didn't float on top of the water, the ice would sink to the bottom, and then the water that's now on the surface would freeze, and that would sink to the bottom. And eventually, the whole body of water would freeze. Whereas typically, only the surface of a given body of water freezes, and it insulates the liquid water underneath from the cold, and the fish and any other life within the body of water are well protected as a result. So seawater, you'll notice, has a density of 1.025 times 10 to the 3. So it's a little bit more dense than fresh water. And if you've ever been in the Dead Sea or the Great Salt Lake, for example, then you know that it's easier to float in those bodies of water than it is in a typical swimming pool. Or maybe you've been in a saltwater swimming pool and you know it's easier to float in the salt water than it is in the fresh water. And the reason for that being is the salt water is more dense. And we'll talk about that relationship when we talk about Archimedes' principle. Blood is mostly made of water, and so you can see the density is a little bit larger than water, but it's not all that different. In fact, the human body in general, being 70% water, has a density that's not all that different from liquid water. And then on the bottom, you go to the gases, and you notice the gases are much less dense. So, so with air, that's 1.29, not 1.29 times 10 to the 3, simply 1.29. So it's about has about 1,000th the density of water. Helium has a lower density than that, and hydrogen, which they don't show, has a lower density still. Carbon dioxide has a higher density. That has to do with a carbon dioxide molecule being more massive than a typical nitrogen molecule. Ultimately, and if you've taken enough physics so far to know about the ideal gas law, that you know that for a given pressure and temperature, the volume of the gas, the volume for a given number of molecules of the gas is always going to be the same regardless of the molecule. So that density depends more or less entirely on the molecular mass of whatever gas you're talking about. So hydrogen with a very low molecular mass has a very low density. The air is 77% nitrogen, 22% oxygen. So its density is more or less proportional to those two. But again, helium is much lighter and has a much lower density, and hydrogen would be much lower still. Steam, well, water vapor is 2 hydrogen and 1 oxygen. So it's going to be lower density than the air is typically. And plus, it's typically at a much higher temperature than the air we experience. So let's go to a quick example. So what is the approximate mass of air in a living room 5.6 meters by 3.8 meters by 2.8 meters? So let's bring up the whiteboard. So the general equation for density is that it's equal to mass times volume. And we are asked for the mass of the air given the volume. And so multiplying both sides by E, you get by V rather, you get the mass is equal to rho times V. We'll assume room temperature rather than 0 degrees Celsius for the room. And so we'll use as a value for the density of the air as 1.22 kilograms per cubic meter. Again, there's no times 10 to the third if you're talking about the air. And then you need to figure out the volume. And assuming the volume or the room is rectangular, as rooms generally are, you can just use the 3 different dimensions that are given. So if you look at that, that's 5.6 meters times 3.8 meters times 2.8 meters. And so you plug those numbers in. And you get a mass of 73 kilograms. So that's not, there are plenty of people who weigh that much or have that much mass. So you might be surprised to see that much mass in a room. But keep in mind, that's typically the amount of air that we interact with. And as we'll see, again, when we talk about pressure, it's not, we don't notice the air when it's what, a density and pressure that it's usually is. We notice it when the density and the pressure change. And we'll talk a little bit more about that in a couple of minutes. So now we introduced density, we're going to introduce pressure right now. And so pressure is the ratio of applied force per unit area. So again, in some circumstances, if you're talking about a section of the air or the air pressure over a region, defining the surface area precisely may be difficult, and measuring the force over a specific surface area may be difficult, but you can still talk about the pressure, the ratio of the two, much like you can talk about the density, the ratio of mass times volume, even if it's not necessarily easy to measure the mass directly or the volume directly. The SI unit of pressure is the Pascal, which is 1 Newton per square meter. So basically 1 Newton of force divided by 1 square meter of surface area gives you a pressure of 1 Pascal. The average atmospheric pressure at sea level is equal to 1.01325 times 10 to the 5 pascals. And that can also be defined as 1 atmosphere, or ATM for short. So that's the average surface pressure at sea level. Basically what that means is that if you go to the beach and you draw a 1 meter square box in the sand, so 1 meter by 1 meter, the weight of the air directly above that square is equal to 1.01325 times 10 to the 5 newtons, or 101,325 newtons. And that may sound like a lot. And again, you might be thinking, well, why don't we feel that? And the reason we don't feel that is because we're used to it. It's what we experience all the time. We feel pressure when it changes. So when we're driving into the mountains, for example, and we're going up hills and down hills and down the hills, you feel the pressure in your ears. And if you're flying in an airplane, you'll also feel the pressure. So let's do another example. Let's estimate, and so this is estimate the pressure exerted on the floor by 1 pointed chair leg, so 66 kilograms on all 4 legs, of area equals 0.020 square centimeters, and a 1,300 kilogram elephant standing on 1 foot. So the surface area is 800 square centimeters. So the elephant obviously weighs a lot more than the chair, but the weight is spread out over a greater surface area. So how does that affect the pressure? And so here you have a chair, and so the chair has a mass, but if the mass is 66 kilograms, then you probably have a person sitting on the chair as well. And you're talking about 4 very sharp legs. So we're interested in the pressure at the points where those legs are in contact with the surface. So let's go back to our whiteboard. So pressure is equal to force divided by area. So the force is going to be equal to the weight of the chair. So that's its mass multiplied by g, and you're dividing by the area. And in this case, the area is given. So you can plug these numbers in. The mass was 66 kilograms. The acceleration due to gravity, and I'm assuming you've taken physics 1 and you've used that number often enough that hoping that most of you remember it, but the acceleration due to gravity is 9.8 meters per second squared. So you multiply those two numbers and you get the weight. And then you need the surface area. So that's the total weight, but it's spread out over 4 legs. So don't forget to multiply by 4. And so you have the areas of 0.020 centimeters squared per leg. Now, you want to convert this, if you want your pressure in pascals, you're going to want to convert this to cubic meters. So 100 centimeters is a meter, which means 1 centimeter is 1/100th of a meter. So 1 square centimeter is 1/100th squared square meters. And so that's 10 to the negative 4, or 1/10,000th meters squared. And so that's the area. So that's the total mass divided by the total weight divided by the total area. So that gives you the pressure, but it gives you the pressure on each leg as well. You're assuming that each leg is bearing an equal amount of the mass to do this calculation. But you do the calculation, and so that's 66 times 9.8 divided by 0.020 times 10 to the negative 4. And what you get is 3.2 times 10 to the 8 Pascal. So, oh wait, I forgot to divide by 4. So that's 8.1 times 10 to the 7 Pascal. So 8.1 times 10 to the 7 pascals. So that's almost 1,000 times the pressure of the air. So quite a bit of pressure. And that pressure comes from very sharp ends on the chair. And so if, not that I recommend trying this, but if you put a chair, if you lay down on your back and somebody put a chair on top and then sat on it, you would feel very intense pressure at 4 different locations. And then we get to the pressure due to an elephant's foot. And it's basically the same idea. It's the weight of the elephant divided by the cross-sectional area. So the weight of the elephant is 1,300 kilograms. And again, you're multiplying by g. And here you're dividing by the surface area of 1 foot, which is 800 times 10 to the negative 4th square meters. So it's a much bigger surface area, but it's also a much bigger mass. And when you do the calculation, what you get is 1.59, or 1.6 rather, to 2 significant figures, times 10 to the 5 Pascal. So again, that's a little bit more than the air pressure, at sea level. But you can see that you actually get a greater pressure with the chair with with narrow legs than you do with the elephant. And even though you would think the elephant has the much greater mass, which of course it does, but its weight is spread out over a much greater area. This brings us to a principle um, developed by Blaise Pascal, for whom the Pascal, the unit, is named. And the Pascal's principle states that a pressure change at any point in a confined, incompressible fluid. So incompressible means its density is constant. So basically, you're talking about liquids unless you're keeping the pressure and temperature absolutely constant, which in general you're not. So when you see incompressible fluids, you're almost always talking about liquids. And so it's transmitted throughout the fluid so that the same change occurs everywhere. So this is an important practical application in hydraulic lifting. If you've ever been in an auto shop, you see what they do to lift the automobile. And so what happens is you exert a force over a narrow surface area. So you get a certain amount of pressure acting down on water. That pressure on the water then gets transferred to the other side of where the water is, and that is a much bigger surface area. So you have the same pressure acting on a much bigger surface area. That makes it possible to lift the automobile. And this is the basic idea behind hydraulic lifting, using water pressure and the constancy of water pressure to lift something that's much heavier than you could lift on your own. And so that's an important practical application of Pascal's principle. The second application, and we'll get back to the whiteboard pretty quickly. The second application of Pascal's principle comes from the pressure of a liquid. And so you can determine the pressure of a liquid, assuming an incompressible liquid, constant density, that you can determine the pressure as a function of the depth h, provided the density of the liquid isn't changing. So how does that work? So again, let's go to the whiteboard. So, and we'll clear this. So you have your liquid. And we'll say we have an object in the water. And we'll make it rectangular because it's easier to explain the math if you're talking rectangular or rectangles. But this applies universally, regardless of the shape of the object in question. So you want to know the pressure acting on the object's surface. And so it's at a depth h. So the pressure is equal to the weight of the liquid that's directly above the object divided by the cross-sectional area of the object. So we'll give the object a cross-sectional area A. And A can be any size you want it to be. It won't ultimately affect the end result. So the pressure is equal to the force, the weight of the liquid, divided by the cross-sectional area over which it's acting. So that's m times g divided by A. Now we can write the mass of the object or the mass of the liquid as being equal to the density of the liquid times its volume. So we can write the numerator as rho times g times v divided by A. Now what's the volume of the liquid that's above the cross-sectional area? Well, that equals the cross-sectional area multiplied by the height. So you can write this as rho times g times A times h divided by A. And like I said before, it doesn't matter what A is. It's going to cancel out, and you're going to get something that applies universally, that the pressure of the liquid at a depth h is equal to the liquid's density, and we're assuming it's remaining constant, times g, the acceleration of gravity, times h, which is the depth of the liquid. And this brings us to another important application of Pascal's principle, and that's measuring the pressure of the air using a column of liquid. So, and an Italian scientist named Torricelli came up with this. So you have an evacuated chamber, meaning all the air has been removed. So there's no air pressure pushing back down on the liquid inside this chamber. And so you have the liquid. And what happens is you have air pressure pushing down on the parts of the chamber that are exposed to the air. And what happens is, since the chamber itself is evacuated, that pushes part of the liquid up the chamber. And the liquid rises until the pressure due to the liquid equals the pressure due to the air. And so that they're balanced out. And so what you get from that is that the air pressure is equal to the density of the liquid multiplied by G multiplied by H. And so barometric pressure has traditionally been measured in terms of inches of mercury, and you still see that in a weather forecast, for example. If they say the pressure is 30 inches today, well, that's the amount, or that's the height to which an evacuated, a mercury in an evacuated column will rise due to the air pressure. And you can calculate what H is, at a pressure of 1 atmosphere. So you can plug in for P air 1.01325 times 10 to the 5, divided by the density of mercury, which is 13.7 times 10 to the 3 kilograms per cubic meter, and then divided again by G, which is 9.8 meters per second, you'll get the height in meters of that column of mercury. And if you convert that to inches, you'll get a number very close to 30. And so 30 is typical air pressure at sea level. And so that's an important practical application. Again, of Pascal's principle. So the pressure of the air acting outside the chamber has to equal the liquid pressure inside the chamber. And so mercury was considered preferable to water because it's quite a bit more dense. It's 13.7 times 10 to the 3 kilograms per cubic meter. So it's about 14 times more dense than water, which means you need a much smaller evacuated chamber, much smaller value of H for the evacuated chamber if you're working with mercury instead of water. Mercury, however, is a very dangerous substance to handle. So modern measurements of air pressure work with different things. It's usually something electronic, but again, mercury is no longer commonly used for measuring pressure because, again, you spill it on yourself, you can make yourself very, very sick. So that's the pressure of a liquid. And I believe we have one example right here before we move on. So estimate the pressure needed to raise a column of water to the same height as a 35-meter tall oak tree. So what's the pressure basically of 35 meters of water? So we'll go back to the whiteboard and do the calculation. So that's the pressure is equal to rho g h. So rho, the density, and so that's the Greek letter rho, that's not the letter P. So that's 1,000 kilograms per cubic meter. So 1,000 kilograms per cubic meter. G is what it always is. And then H is, I think, 35 meters. Let me double check that before I do the calculation. So 35 meters. And so you plug those numbers in, and you get 3.4 times 10 to the 5 Pascal. So notice it's quite a bit more dense than air pressure. In fact, it only takes 10 meters of water to produce the same amount of pressure. And 10 meters, a 10-meter height of water to produce the same pressure that the entire atmosphere does. So again, that gives you some idea of the differences in density that are involved. So it's 3.4 times 10 to the 5 Pascal. This brings us to one of the oldest principles in physics. And the principle was developed by a Greek living in the island of Sicily. His name is Archimedes. He was well known at the time for his exploits as a military engineer. Sicily was fought over by a bunch of different people, the Greeks, the Romans, the Carthaginians. They all carved out a chunk of Sicily, and so battles were common, unfortunately. But Archimedes was in the middle of all that. But he was also, one of the first great physicists. And again, he devised a principle that still holds up more than 2,000 years later. And it basically relates the upward force acting on an object immersed in a fluid to the density of the fluid itself. So what he figured out was that if you submerge an object in water, the object doesn't fall, doesn't fall to the surface at an acceleration of 9.8 meters per second squared. So it doesn't fall at anywhere near the same rate that a rock in the air would fall, for example. So there has to be some sort of upward force acting on it. And so Archimedes figured out what that buoyant force is. And we can show that, again, going back to the whiteboard, we can visualize what's going on. So you have a liquid. It doesn't necessarily have to be water, but for the sake of simplicity, we can assume it's water. So we have our rectangular object. And again, the object doesn't have to be rectangular. It just makes the math simpler. And but the equation applies universally. So the top of the object is at a depth h below the water, or below the surface. And the object has a thickness of delta h. So the pressure acting on the top of the object is going to be less than the pressure acting on the bottom of the object. And because the object is lower. And so you have a downward pressure acting on the top surface. And we have an upward pressure acting on the bottom surface. So pressure acts on all sides of the object, and it acts inward on all sides of the object. We're not going to be worried about the pressure on the sides of the object or on the horizontal faces of the object. Those will cancel each other out. But the upward pressure is going to be greater than the downward pressure. And again, the reason for that is because it's at a greater depth. And so the pressure at that depth is going to be greater. So we'll define the buoyant force as the net pressure force. And so that's equal to P up minus P down times the arbitrary surface area A. So the upward pressure is equal to rho times G times H plus delta H. And you're subtracting from that the pressure at the top of the object, which is rho times G times H. And you're multiplying all that by the cross-sectional area A. And what you get is that's equal to rho times G. You do the math, only the H terms cancel out, but the delta H term is left, times A. So delta H times A is the volume of the object, or at least the portion of the object that's submerged. So that's rho times G times the submerged volume of the object. So in the drawing, it's completely submerged, but it doesn't have to be completely submerged. An object that is floating on the surface is only going to be partially submerged. And we'll talk about that in more detail in a couple of minutes. But the buoyant force acts on the volume of the object that's under the surface, that's submerged. So the net force then is equal to the buoyant force minus the object's weight. So gravity is still acting. So there's the upward force and there's the downward force. So the way Archimedes explained it, the buoyant force is equal to the weight of the fluid that would otherwise be occupying the space where the object is. So it's the weight of the fluid that's been displaced by the object. And so that's equal to the density of the fluid times G times, again, the volume of the object, or the volume of the object that's submerged or under the surface. The net force is equal to the buoyant force, which is the density of the fluid times G times the submerged volume, minus the weight, which is M times G, which you can write as the density of the object times G times the volume of the object. Now, if the object is completely submerged, the net force is just going to equal the density of the fluid minus the density of the object. So that difference multiplied by G multiplied by the volume of the object. So what's that telling you? Well, if the density of the fluid is greater than the density of the object, the net force is positive, which means the net force is upward. The object will rise to the surface and float. If the density of the object is greater than the density of the fluid, the object will sink. So whether an object floats or sinks in a fluid depends on whether it's more or less dense than the fluid. If it's more dense, it will sink. If it's less dense, it'll rise to the top and float. So that brings us to another example. What fraction of a piece of iron will be submerged when it floats in mercury? Now, if you submerged a piece of iron in water, it would sink because iron is more dense than water, but iron is not dense as mercury. So the iron is less dense than mercury. And so we're going to draw a piece of iron. Again, we'll make it nice and rectangular. And it's only partially submerged. So you have the buoyant force acting upwards, and you have the weight of the object. And so the liquid is mercury and the object itself is iron. So, and the weight of the object acting downward. Now, if it's floating, those forces are in balance. They're equal and opposite to each other. So the buoyant force is equal to the density of the fluid, which is mercury, times G times the submerged volume. Remember, the buoyant force only acts on the portion of the object that's submerged. And that's equal to the density of the object. So that's the density of the iron times G times the volume of the object. So the G terms cancel out. And so we are asked to find the fraction of the piece of iron that's submerged. So basically the ratio of the submerged volume to the total volume of the object. And so you divide both sides by the volume of the object. You also divide both sides by the density of the mercury. You get the ratio you want. The submerged volume to the object's volume is equal to the density of iron divided by the density of mercury. And that's Hg, not He. He is helium, which is a lot less dense than iron. So, so you have the ratio of these two densities. And so if you go back to the table I showed earlier, or a similar table, the density of iron is 7.8 times 10 to the 3 kilograms per cubic meter. The density of mercury is 13.6 times 10 to the 3 kilograms per cubic meter. And so you plug those numbers in, you don't need the times 10 to the 3, and you get 0.57 or 57%. So you put the iron in mercury, and again, we're ignoring any waves or any bobbing up and down that can sometimes happen. We're assuming it's resting peacefully on the surface, and 57% of the iron rather will be submerged in the mercury, but the remaining 43% will be above the surface. And that's basically how that works. So you can use Archimedes' principle to talk about the ratio of the submerged portion of the object to the total volume of the object. So move on to another example. And the lab experiment is going to be similar to this. We're not going to be working with moon rocks. We're going to be working with a piece of aluminum. But it's the same idea as far as going through the steps to calculate the density of the aluminum, given what you know about its weight when you suspend it in the air and its weight when you suspend it in water. So when you suspend it in water, it's going to have an apparent weight. In this particular example, we talk about an apparent mass. So the apparent weight is equal to the apparent mass multiplied by G. And so we're asked for the density of the rock. So again, we go back to the whiteboard. And we're just given two quantities. We are given that the actual mass of the moon rock, and if you have a scale that's easy enough to work with, is 9.28 kilograms. And the apparent mass is equal to 6.18 kilograms. So we're asked, what is the density of the rock? So we know that the apparent force, well, in case we don't know that yet, I'll show you what's going on. So you have some sort of spring scale, and then you have an object of mass m. Now, if you're just holding that object of mass m in the air, you're going to get a force reading that's equal to m times g. If instead of holding it in the air, you're suspending it in the water, you're getting what's called an apparent mass. So you're going to get a lower mass reading than you normally would. So why are you getting a lower mass reading? Well, you have the upward buoyant force and you have the downward force due to gravity. And so the reading that you get from the scale, or the apparent force, is equal to the object's weight minus the buoyant force. So this relationship only applies when the object is more dense than the water and would otherwise sink. So the apparent force is equal to the object's weight minus the buoyant force. And so we can write this: the apparent force is equal to the apparent mass times g. And that's equal to the actual mass times g minus the buoyant force, which is the density of water times g times the full volume of the object. So that's capital V. But we don't know what the full volume of the object is, but we don't need to know that. Remember, density is equal to mass times volume. So the volume, just flipping the rho term with the V term, the volume is equal to the mass divided by the density. So you can write this as the apparent mass is equal to the actual mass, and we're dropping the g terms out, minus the density of the water times V, which is the mass, divided by the density of the rock. So we'll call that rho sub r. And so we can write that, factoring out the m, as m times 1 minus rho w over rho r. So we know that the density is greater. The density of the rock is greater than the density of the water. We need to figure out how much greater. So we're going to need to do a little bit of algebra to solve for the density of the rock. So the first thing we're going to do is multiply, or divide rather, both sides by m. So the apparent mass divided by m is equal to 1 minus the ratio of the densities. And so you can then flip the density ratio with the mass ratio. So this becomes the density of the water divided by the density of the rock is equal to 1 minus the ratio of the apparent mass to the mass of the rock. And we want to solve for rho r, so we just multiply both sides by rho r and then divide both sides by the term on the right. And what you get is rho r is equal to rho w, the density of the water, divided by 1 minus the ratio of the apparent mass to the actual mass. And that's something you can then work with. So the density of water, as always, is 1,000 kilograms per cubic meter. And in the denominator, you have 1 minus 6.18 kilograms divided by 9.28 kilograms. And so you plug all those numbers in. And what you get to 3 significant figures is, we'll write it down here, 3.00 times 10 to the 3 kilograms per cubic meter. So that's how you solve that problem. So there are a few steps, but You just need the weight of the object in the air and the weight of the object when it's submerged, and that's enough information to give you the density of the object. And so there's a legend with Archimedes, that he understood that, and that his king had been presented a gold crown as a gift, but Archimedes took the crown, weighed it outside the water, and then weighed it inside the water, figured out the density of the crown, and he realized it wasn't gold. So his king had been fooled and was not happy. But that's one of the legends surrounding Archimedes, as far as what he was able to do at a time when, to be honest, math and physics were not very well advanced. So now we're going to move on to continuous motion, or when you have a incompressible fluid. And so constant density, it generally means a liquid. But if the pressure and temperature are maintained constant throughout the whole process, then it can mean a gas as well. But generally, when you're talking about a fluid of constant density, you're talking about a liquid. And so it's flowing continuously. And through a pipe, the pipe's cross-sectional area can vary. So the amount of mass flowing past one point on the pipe per unit time equals the amount of mass flowing past any other point on the pipe per unit time. So the flow is continuous, and basically, in order for things to keep moving at a steady rate, you need the same mass flowing past any point in the pipe per unit time. Now, if the density is constant, that means the volume of the fluid is also constant. And that makes it possible to develop some relations. So we'll start with the basic example where we have a fluid. It has a cross-sectional area A1 and a cross-sectional area A2 in the narrow end of the pipe. So we have point 1 and we have point 2. We have the pipe, and so you have point 1 on the wide end of the pipe and point 2 in the narrow end of the pipe. And so we're told that the mass flowing past point 1 per unit time is equal to the mass flowing past point 2 per unit time, where if the densities are constant, that means the volumes are, the volume flowing past point 1 per unit time is equal to the volume of fluid flowing past point 2 per unit time. So it's the same delta capital V over delta T. So capital V is for volume. So how do you figure out what the volume is? Well, over a given amount of time, you can write this as area 1 times delta x1. So the fluid travels a distance delta x in the time delta t. And that's equal to A2 times delta x2. Again, so in this segment, or in the narrower segment, it travels a distance x2, or delta x2, in the time delta t. Well, delta x over delta t is simply the velocity, or small v. So you can then write the continuity equation as A1 times small v1 is equal to A2 times small v2. So the product of cross-sectional area and velocity is conserved in continuous flow. And that product is also equal to the volume rate of flow. Again, constant density, the volume of fluid passing a given point over a time delta t is going to be the same for any point in the pipe or in the network of pipes. Okay, so that will bring us to an example ultimately. But let's just finish with this. The density is constant. The volume of the fluid passing through one point equals the volume passing through any point in a given time delta t. And the volume rate of flow can be expressed as the product of the cross-sectional area of the pipe and the velocity of the fluid in that section. So the continuity equation is basically A1 V1 is equal to A2 small v2, excuse me. And either of those products is equal to delta capital V over delta T, which is called the volume rate of flow. So with that, let's move on to an example. So we have a 15 centimeter radius air duct is used to replenish the air of a room 8.2 meters by 5.0 meters by 3.5 meters every 12 minutes. How fast does the air flow into the duct? So again, usually when you're talking about the continuity equation, you're talking about a liquid because the liquid's density is constant. Here you're assuming the pressure and the temperature within the room are held constant. So it's that the pressure of the air coming into the duct is also, or the air coming in through the ducts is also the same pressure and the same temperature, so that the density doesn't actually change. And in that case, the continuity equation will apply. So we're given the volume of the room and the amount of time it takes to fill the volume of the room with air. Or to replenish the volume of the room with air. So that's delta capital V over delta T. And so that's going to equal the area of the duct, or the cross-sectional area of the duct, which we have the means of calculating, multiplied by the velocity of the air, which is what we're asked to solve for. So let's set that up on the whiteboard. So let's visualize this with a diagram. Say we have a room, and we say we have a duct, and the duct has a radius r. And so the air comes down through the duct and out into the room, and we know the dimensions. So delta capital V over delta T is equal to the cross-sectional area of the duct multiplied by the velocity of the air through the duct. Now, it's a circular cross-section. If you're given a radius or a diameter, you can assume a circular cross-section. And so it's a 15 centimeter radius. So we can write the area as pi r squared, and then multiplied by V. So then V, you divide both sides by pi r squared, is equal to, and then multiplied by delta capital V over delta T. So we have the means of solving for the velocity. So that's 1 divided by pi divided by, that's 15 centimeters. And again, you want to write everything in SI units if you want your velocity in meters per second. So that's 0.15 meters squared. So again, 15 centimeters. And you're multiplying it by the dimensions of the room. So that's the volume. So that's 8.2, 5.0, 3.5. And then you're dividing by delta t. So you want this in seconds. It's given in 12 minutes. So you're going to want to multiply the 12 minutes by 60. And that gives 720 seconds. And so now we have enough information to plug in the numbers and solve the problem. So 8.2 times 5 times 3.5 divided by pi divided by 0.15 squared, and then divide it by 720. And that gives 2.8 meters per second. So that's the speed of the air coming in through the ducts. So that's basically how the continuity equation works. So now we are going to extend our discussion of continuous flow further. So we have the continuity equation, which is ultimately an expression of the conservation of mass. Now, what we're going to do is talk about the conservation of energy. And so this equation that comes out of this is called the Bernoulli equation. So now we have pipes with fluid of constant density, continuous flow, but now the height of the pipes can vary, which means the potential energy of the liquid flowing through the pipes can change. And then the kinetic energy can also change. And we're also going to allow the pipes to be open at either end so that there's a pressure acting inwards from both sides. So how does this look? Going back to the whiteboard yet again. So you have your pipe. The center of the pipe is at Y1. And the center of this pipe is at Y2. So you have a velocity V1 and a velocity V2. You have pressure acting into the pipe from both sides. So you have P1 and P2. So pressure, so again, pushing in from both sides. So how does this look in terms of energy conservation? Well, going back to first semester physics, for a non-conservative force, and the pressure force is non-conservative, the work done by the non-conservative forces is equal to the change in kinetic energy, which we'll call delta K, plus the change in potential energy, which we'll call delta U. So how do you figure out the work done? Well, the work done is equal to the force times the distance. So you have positive work, assuming the flow is right to left. You have positive work on the first side. So that's the pressure P1 A1 times delta X1, so the distance. And that's equal to, or subtracting from that, P2, and it's subtracting because here the pressure force is acting in the opposite direction of the motion. So it does negative work. So that's P2 times area 2 times delta X2. And so delta X is the distance the fluid travels over a time delta T. And so that's equal to the change in kinetic energy, which is 1/2 times the mass of the fluid times V2 squared minus V1 squared, plus the change in potential energy, which is the mass times G times the change in height, which is Y2 minus Y1. So that's the statement of energy conservation. We can simplify this a little bit. If you remember, it's continuous flow, so the continuity equation holds, which means the volume of fluid passing through, passing a given point in a given amount of time is going to be the same on both sides, or anywhere on the pipe. So you divide by that volume, you get P1 minus P2. And here you have mass, but you're dividing by volume, that's just the density of the fluid. So this becomes P1 minus P2 is equal to 1/2 times rho times v2 squared minus v1 squared, plus rho g times y2 minus y1. And so that's the basic form of the Bernoulli equation. If you want, you can write it so that you have all the terms for section 1 on one side of the equation and for section 2 on the other side of the equation. So you have P1 plus 1/2 rho V1 squared plus rho G Y1 is equal to P2 plus 1/2 rho V2 squared plus rho G Y2. So you basically have a conserved quantity. So the pressure acting at a given point plus 1/2 times rho times the velocity at that point plus rho times g times the height at that location is a conserved quantity throughout the pipe, or throughout the system. So with that, we'll do a fairly basic example, and then we'll be done for today's lecture. So we have a 6.0 centimeter diameter horizontal pipe gradually narrows to 4.5 centimeters. Notice they don't say anything about height, so we can assume we don't need to worry about potential energy in this example. When water flows through the pipe at a certain rate, the gauge pressure in these two sections is 32.0 kilopascals and 24.0 kilopascals respectively. So we have a means of measuring the water pressure, or the pressure acting on the water on either end of the pipe. And then we're asked, what is the volume rate of flow? So you're going to need two equations to solve this, the Bernoulli equation and the continuity equation. In fact, you'll need multiple forms of the continuity equation to solve this. But let's set this up. First, we'll set up a diagram. So not perfectly centered, but it'll do well enough. And so we're told it's a 6.0 diameter horizontal pipe. And it narrows down to 4.5 centimeters. And that's the diameter of the pipe. When water flows through the pipe at a certain rate, the gauge pressure is 32.0 kilopascals and 24.0. And so we're asked to find the volume rate of flow. So the volume rate of flow is delta capital V over delta T, and that's equal to A1 V1, and it's also equal to A2 V2. So we have enough information to figure out A1 or V1, but we'll need, or rather A1 or A2. We'll need either V1 or V2 to solve for the volume rate of flow. So how do we do that? Well, we go back to the Bernoulli equation. That's P1 minus P2 and that's equal to, again, we don't need to worry about potential energies, but it's still 1/2 times rho times V2 squared minus V1 squared. So we basically have two equations with two unknowns. We don't know either V2 or V1, but we can use the continuity equation, or at least this portion, A1 V1 is equal to A2 V2. And we can use that to solve for one of these in terms of the other. So let's write V2 over V1, or rather V2, is equal to A1 V1 over A2. Now, you can write this as V1 times pi R1 squared over pi R2 squared. The pi terms cancel out. We're not given the radius values, but we're given the diameter values. And the radius is always going to be half the diameter, which means if you're talking about the ratio of the radius values, the ratio of the diameter values is going to be the same thing. So you can write this as V1 times D1 squared over D2 squared. So we now have a means of, we now have V2 in terms of V1. That makes it possible using the Bernoulli equation to solve for V1. So we have P1 minus P2 is equal to 1/2 rho times V2 squared, which is V1 squared. And then notice you're squaring the square. That becomes D1 to the 4th power over D2 to the 4th power minus V1 squared. So you can write that as being equal to 1/2 rho V1 squared D1 to the 4th over D2 to the 4th minus 1. And now you have the means of solving. So V1 is equal to, you have 2 times P1 minus P2. So you multiply both sides by 2. And then in the denominator, you're going to have that ugly term, D1 to the 4th over D2 to the 4th minus 1. And then you're taking the square root of that whole thing. So how does that look with numbers? So that's 2 times 24 minus 30, or 32 minus 24 is 8.0 kilopascal. And so that's D1 fourth over D2 fourth. So that's 6.0 centimeters over 4.5 centimeters. And you're taking that whole thing to the 4th power minus 1. And so you plug all those numbers in. Don't forget a kilopascal, that's 8,000 pascals. So 2 times 8,000 divided by and then you take the square root. Something doesn't look right. Hold on. 2 times 8. Okay. Oh, I'm forgetting the row term. That's where I'm missing a term. So V1 is 2 times P1 P2, and don't forget the row term here. And so you've got this times 1,000 kilograms per cubic meter. I apologize for the oversight on that. Okay. Yeah, so you need the row term in as well. And that gives 2.7 meters per second. So that's what V1 is. We still need to solve for the volume rate of flow. So that only gives us a little bit of this. So I'm going to erase the drawing right now so we have space to work with. But we want the volume rate of flow, and that's going to equal A1 times V1. So delta capital V over delta T is equal to A1 times V1. So that's pi times R1 squared. So the diameter of the wide circle is 6.0 centimeters. So the radius is 3.0 centimeters. So we'll write that as 0.030 meters squared. So that's the area, and you're multiplying that by 2.7 meters per second. And that gives the volume rate of flow. And so that's 7.7 times 10 to the negative 3 cubic meters per second. So there were multiple steps in that problem, but ultimately it's possible to solve for the volume rate of flow using the Bernoulli equation. So the continuity equation lets you solve for V2 in terms of V1, leaving only one variable or leaving only one unknown in the Bernoulli equation, so you can solve for V1 and then multiply it by A1, its cross-sectional area, to get the volume rate of flow. So that's chapter 13. So in the next class, we'll be going over problems. And so you'll be each assign a group who is going to work, or you're going to each be made part of a group that's going to work on a particular problem. And somebody from the group is going to present a solution online. So be prepared to work together with that. If you are in any way, shape, or form uncertain about your answers, uncertain about how to proceed with your particular problem, email me. If you want to talk in person, we can schedule a Zoom meeting. But that's how it's going to work in this class. So with that, I will stop for now. And we will resume this at our next discussion. Okay, thank you very much.